Today's lecture, we're going to start going through some of the fundamental operations in machine or in assembler. So obviously simple things that we'll be using frequently are kind of multiplication, addition, things like that. So we're going to go through those basic primitive maths operations in this class. And then in the next lecture, we're going to get a little bit more technical and start working on bitwise operations. So far all we've actually been able to do is move values in and out of registers. So it's not very complicated program. So we need to add a little bit more structure. And in this lecture, we're going to discuss integer maths. So all of the operations that I'm going to go through only work on integers. Now, going forward, when we get to floating point numbers, you'll see that there are specialized instructions for that. But for the moment, assume that we live in the realm of only integers. So the first operation I'm going to go through is the negation operation, and it's indicated using the mnemonic neg in assembler. And all that neg does is it converts a number to its 2's complement. So exactly as you would have learned in chapter 2, and you would have actually learned already in first year, where we will flip all the bits and add 1. That's what happens to us when we use neg. Now later on, there's another operation in the next lecture called not. What not does is it flips all of the bits. Please do not get confused between not and neg. Neg changes the sign, so neg is basically equivalent to multiplying by -1. So let's say RAX, for example. So neg multiplies by -1. It's not the same as the not operation. Now, neg also does a couple of things when used. Well, the first thing I should mention is neg only takes one operand, and that is both the source and the destination. So in this first instruction over here, we're negating a 64-bit value and storing the result in RAX. So simply changing the sign. So a one operand instruction. Something else that neg, however, does is it sets certain flags, and you'll see this is a trend with a lot of assembler instructions, is that the result of the computation can have an effect on an array of flags. Now, in the case of negation, the two flags that are affected and that are relevant to us is the sign and the 0 flag. So the 0 flag will set if the result of the operation resulted in a 0 value, and the sign will be 1 if it became a negative number, or 0 if it stayed as a positive number. So those are the two flags that are going to be important to us, and you'll see we're going to use them even at the end of this lecture when it comes to conditional jumps, conditional moves rather. But we'll be using those flags for proper kind of control structures going forward. So if statements, loops, all of that will rely on these kind of flags. Now, the negation operation also depends on the size of the register that you provide. So in this first example, it was a 64-bit register. If, for example, I use negate on a 32-bit register, we end up in a situation where we'll negate the bottom 32 bits so of the 64-bit register. So here's EAX, and this whole chunk is RAX. If we call neg on EAX, so this part over here, we'll perform 2's complement, so all the bits will be flipped and we add 1, and then the top 32 bits of the 64-bit register will be 0 extended. So even though you didn't think when you were making this instruction call that you're going to affect the higher order bits of the whole 64-bit register, it is, as I mentioned in the previous lecture, a kind of feature of 32-bit instructions that it always 0 extends the higher order bits. We then can also work on smaller size registers. So if I want to do a negation on just a 16-bit register, so AX, works as before, performs 2's complement, but it doesn't 0 extend. Okay, it just affects that 16-bit. Same thing applies if I want to, for example, negate AL, it will simply perform the 2's complement, or the negation operator on the 2's complement number for AL. It will not affect the higher order bits. It's only this special case here with the 32-bit register where we get that 0 extension feature. Now, that instruction that you saw over here was using registers, but we can also perform negation directly on pieces of memory. The only difference now is that, remember from the previous lecture, I said that if there's no way that the assembler could infer what the size of the data is, you would need to somehow specify it. So if I were, for example, to simply write neg x, where say x was a label of something in my data segment. So let's say x was a data quad, and let's say it was 73. Now, if I just had this instruction in isolation, there's no way for the assembler to know how big x is. I know how big x is meant to be because I defined it, but the actual assembler doesn't know. So I always need to tell it how big a piece of memory x actually is, which is why in the case of this example I wrote up, we'd have to specify the size, which is a Q word. Okay, so it's a quad word, so 64 bits or 8 bytes. Same thing applies if x happened to be a double data word, then I would need to use D word. If it was a data word, I'd have to use word. And if it was simply a data byte, I would have to use the byte keyword. So again, you can immediately look at an instruction like the one over here and say, wait, how would the assembler know how big it is? It can't, there's not enough information in that instruction by itself. So we need to tell the assembler how big x actually is when it performs this operation. Obviously, we would like to perform something more complicated than simply multiplying by -1. So the next instruction we're going to go through is the add instruction. The add and the subtract instruction work pretty much in the same way. They both have two operands where the right-hand side is the source and the left-hand side is the destination. So if I have something like add RAX, RBX, the one on the right-hand side is the source, and the one on the left-hand side is the destination. And what actually ends up happening here is RAX will get set to RAX plus RBX. Now, something to keep in mind is, you will recall from the last lecture, is that I mentioned that we work with Intel assembler. So the Intel way of writing these instructions always has the source on the right-hand side and the destination on the left-hand side. If we were, for example, using AT&T, we would be on the other side of the equation where the source and the destination are actually swapped. So if you read code that's in AT&T version of assembler, things will get confusing because the source and the destination are always the other way around. But for our purposes, you don't need to worry because we're only going to be focusing on Intel assembler. I bring it up primarily so that you don't get confused if you find examples online. Now, the source, so basically the right-hand side, can be a couple of things. We can either have it to be an immediate value, so again, a constant in assembler. We can also have it to be a register, and we can also have it to be somewhere in memory. Okay, so the source can be a constant, a register, or some kind of location in memory. However, the destination cannot be an immediate value. It can only be a register or a memory location. I mean, this makes perfect sense because you obviously couldn't assign a variable to some kind of constant. You could not in normal language go, for example, 6 equals a. That would not obviously fly in C++, and the same thing applies in assembler. So the left-hand side, our destination register, cannot be an immediate value. The one thing you have to actually, however, avoid doing with the add instruction, and the same applies to all assembler instructions, is that you cannot have both the source and the destination being in memory. So an instruction like is not permissible in assembler, and it will not work. If you try and implement it, you'll get an assembler error thrown at you, and it also tells me that you actually haven't implemented any of these kind of instructions in practice. So you can never use both a source and a destination as memory. You're perfectly able to have one or the other be memory, but both can never be memory. At least one has to be, in fact, in either an immediate value or a register. You cannot have two memory accesses. Okay, so this general pattern applies to all x86 instructions. So let's look at a couple of extra details to keep in mind with the add instruction. Now, the add instruction also, like the neg instruction, sets certain flags. It sets quite a few flags, but the important flags for us are as follows. The sign flag, so did the result of the addition result in a negative number? The zero flag, the overflow flag, so is the number that, for example, we're trying to store after the addition larger than the capacity of the register? And there are a couple of others, but we'll use mostly these three when we kind of use conditional moves and things like that. Now, there's no distinction between a signed add and an unsigned add because the logic is identical because we use a 2's complement system. We do also have available to us an extra variant of add, which is kind of the simplified increment. So we have a single operand instruction called inc, and all that will basically do is it's going to set rax to be equal to rax plus 1. Okay. In principle, you don't actually ever have to use inc. You can always simply add 1, but it's good to know it's there. And as with the previous single operand instruction, if you want to try and increment directly into memory, you have to specify the size. Because once again, if I had instruction just like this, there's no way for the assembler to know what size X actually is. So we need to kind of specify the size in that situation. Otherwise, it won't work at all. Okay. So let's write a very simple program. I'm using an example quite similar to what's in the book, but I'm just explaining what we want to achieve, and then we look at the assembler. So all we want to do is we have 3 variables stored in our data segment, a, b, and sum, and we want to increment a by 9. So we want to set a equal to a plus 9, and then we want to set sum to be a plus b plus 10. So kind of rudimentary operations, but it serves as a good example for how to use sum. So first things first, you'll see here, again, this is an example that's linked using GCC because I have main as my entry point and I'm returning. And again, this XOR command here is simply setting rax to be 0, which is the return value. But the important bit for us at the moment is this chunk over here. Okay, so we have our 3 variables, a, b, and sum, and we want to try and perform our calculation. So remember, the first thing we wanted to do is I wanted to set a equal to a plus 9. So this one over here. And then I wanted to set sum equal to a plus b plus 10. Okay, so this one over here. So first thing I'm going to do is I'm going to move the immediate value 9 into rax, and then I'm going to add what is in rax to a. So after this, a is in fact going to be a plus 9, and the result is stored directly in memory because our source register pointed to the location in memory. Okay, so we've basically achieved goal 1 already, and now we want to move on to the second one where I want to add a, b together and then add 10 on top of that. So first thing I'm going to do is I'm going to just pull b from memory into a register. So I'm going to load from b into a, or rax rather. So rax will now contain the value 310. Then I'm going to simply add 10 to what is in rax. So in essence, I'm doing this part of the calculation first. And then lastly, I'm going to add what was at location a into rax. And I basically perform this last little chunk here. So I've added a. Now all I have to do is move rax back into sum. So now I'm going to move from rax back into sum. And I've achieved what I wanted to achieve. Now, this is a good example of where you might have kind of made your mistake in that you might have, for example, tried, because you see sum is 0, you might have tried to do something like add sum a. Now, obviously, this makes the assumption sum was 0 to start with, which it is in this case. But the bigger issue is that this instruction will not execute because we have 2 memory accesses, so we cannot do it. This is why you constantly see us moving things into registers to make certain operations possible. Now moving on to kind of the mirror of addition, we have the subtraction operation, and again performs integer subtraction. It takes 2 operands, a source and a destination, and it sets the same flags as our addition instructions. So we have the sign flag, the 0 flag, and the overflow flag. And once again, we do not distinguish between signed subtraction and unsigned subtraction. The logic between the two is the same. It uses the same machinery on the CPU, so we don't need to make a distinction. Let's see an example of using this. So again, we have some variables in our data segment, so a, b, and diff. And we now want to perform the series of operations. I want to subtract 10 from a, subtract 10 from b, and then store the difference between a and b into the variable diff. So let's try and actually do this. So again, we just want a to be a minus 10, b equal to b minus 10, and we want diff to simply be the difference between the two. Okay, so I'm just rewriting this for convenience so you can look at it as we're going. So first thing I want to do is I want to subtract this 10. So I'm going to move 10 into RAX, so it's ready to go, so I can subtract it from my memory locations. I'm then going to subtract 10 from A and store the result in A. I'm then going to subtract 10 from B and store the result in B. So basically we've achieved task 1 and task 2 already. And the last thing I need to do is do that subtraction and store the result in div. So I'm going to pull B out of memory and put it into RAX. Then I'm going to subtract A from RAX. So in essence, I'm basically setting RAX to be B minus A. And then all I have to do now is move RAX back into div. Now again, this is clearly linked with GCC because of using main as our entry point. You'll see here I've just made it a little bit more explicit that I'm moving 0 into RAX. This is kind of equivalent to actually just doing XOR RAX. I'll explain why that actually works in the next lecture, but for the moment, just you can believe the fact that XORing a variable with itself is the same as setting it to 0. Cool. So now we can try and do something that's a little bit harder to achieve in assembler, or at least one variant of achieving it is slightly harder in assembler, and that is to perform multiplication. Now, there is actually a distinction between signed and unsigned multiplication in assembler, and the same thing applies to division. So unlike addition and subtraction, where we only had one instruction, we now have two instructions to perform multiplication, or two types of instructions rather, to perform multiplication, and the same thing applies with division. So the way in which you can distinguish the two is that we have MUL for unsigned multiplication and IMUL for signed multiplication. Now, mul actually is a far more limited instruction in that there's only one way of using mul. IMUL actually has multiple variants, and in practice, unless you're very constrained on space, IMUL is by far the easier of the two to use. But it's good that you understand how to use both mul and IMUL. So this is how we can use mul. First thing to note is that mul only has one operand. Okay, so it only takes one parameter, which is the source parameter. Now you're going to be asking yourself, okay, if a multiplication only takes one operand, what is the other component of the multiplication? I mean, if I have A times B, clearly there are two things here. There's the first and the second. So what's the other component in the multiplication going to be? Now the way in which assembler does this is the other factor is what is stored in RAX if we're performing a 64-bit multiplication. So in essence, if I have an instruction like mul RBX, what will end up happening is I perform the multiplication RAX times RBX. Okay, so that's the multiplication that will happen. Now you'll see here that if instead of using a 64-bit register, I was actually performing a multiplication against a 32-bit register, the other factor would be what's in EAX, not in RAX. And the same thing applies if I was multiplying, say, for example, mul, so let's just say BX, what will end up being multiplied will be AX times BX, okay? And lastly, the same thing applies for our very small 8-bit register as well. Now, the destination of this is also kind of unclear at this first point because we only have one operand, and I said it's the source operand, so that register is not going to get changed. So what does get changed? Well, the result of the computation actually gets stored in two registers for all cases except one. So if I, for example, multiply a 64-bit register by a 64-bit register, it's very possible that I end up getting a register that is much bigger than 64 bits. So the result of that computation needs to actually be stored in 128 bits of space. So the way in which this is achieved is that the result of the product is actually stored into two registers. So in the case of a 64-bit multiplication, the higher order bits will be stored in RDX and the lower order bits will be stored in RAX. So basically we have a bunch of numbers. So the top order bits, this will live in RDX, and the lower order bits will be stored in RAX. Now, for a lot of the kind of multiplication you may perform, you don't need to worry that much and that most of your answers will fit in RAX. But there's two reasons you need to be aware of this. One, if the result is larger than 64 bits. And two, whatever you had in RDX is going to be affected by performing this multiplication. Okay, so if our answer perfectly fitted in here, so say it was a positive number, so say it was 5, and then we can just store that with a nice bit of binary. then it will just be zeros in the higher order bits, including RDX. So though you don't think you're affecting RDX by performing the multiplication, it does actually get changed. So it's something to keep in mind. Now, here's just a little example to illustrate how this works. So I'm going to load a value into RAX. So you'll see I'm loading something into RAX, which means I'm loading 64 bits of value from A. So A would have to have been defined like this. So let's say it's 105, for example, but it would have to have been defined using a data quad. I then perform my multiplication. Now, I can use a register in this mul, like I have in my examples, or I can use a specific location from memory. So now in this example, I'm going to be using something from memory. And again, I can't just go mul B because the assembler doesn't know how big B is. So I have to specify its size. So in this case, I'm going to say, well, I want B to be a quad word. So assumedly B is stored like this in memory as a data quad. So I have to specify the size. Okay. I can also perform similar kind of operations if I'm working with a 32-bit value. So say I want to multiply C and D, and say C and D are also defined like this. So these would be double data words in my data segment. I can now move C into EAX and then multiply C by D. And then the result of which will be stored in this combination of two registers, EDX and EAX. Now, the one place that this double register output doesn't apply is if I multiply two 8-bit numbers. So say I multiply AL by BL, the result will all exist in AX. So it's kind of a special case to consider. But for all the other larger sizes, the result is always going to live in two registers. Now, this is a place where it can be kind of confusing in a sense because you might be under the apprehension, if we look at this example over here, that if I multiply two 32-bit numbers together, my answer could fit into a single 64-bit register. And in principle, it could. However, the design at the time, when they designed the 32-bit instructions, we only had 32 bits of space in a register, which is why they decided that the result has to exist in those two registers. So instead of changing how it worked when they extended the instruction set to 64-bit mode, they kept that design decision. So even though in principle it would be possible that the whole answer could live in one register when I multiply two 32-bit numbers together, so it could live in one 64-bit register, in practice it still is split across two 32-bit registers. So that's something that you must just kind of keep in mind. It's not an optimal design, but it's a result of making sure the instructions are perfectly backwards compatible, so they still behaved in the same way as we did extensions. So how do we perform signed multiplication? Well, as I mentioned earlier, we have a slightly different instruction, which we call imul, to indicate it's a signed version. And we can use imul in precisely the same way we used mul, with a single operand version. Or we can use the easier to use version, which has two operands. One is a source and a destination, and it behaves exactly like multiplication and subtraction. Okay, so we don't need to worry about it affecting us adjacent registers at all. It will only affect the two that are present inside the instruction. So here, for example, I'm multiplying RAX by 100 and storing the result in RAX. So it will simply be RAX is equal to RAX times 100. Now, the downside with this approach is that if your answer is larger than 64 bits, or larger than the size rather of the destination register, you kind of lose the data. You're going to get overflow, and your answer, you're going to lose those higher order bits. You're going to get an answer that doesn't make sense. So if you know, or you have a suspicion that your answer is going to be larger than the size of the registers, you need to use the single operand version to get that functionality. Okay. Now, just as a general kind of note, there's a variant as well available to us of this multiplication, which is the 3 operand form. And basically what this does is it says let's R8 equal to R9 times the last parameter, so in this case 11. But it's a very restricted version of an operation because this third operand can only be a constant or an immediate value. So you can't, for example, put another register there or a memory location. It has to be a constant. So this third case does come up sometimes, but by and large, you can get away with just using this version, where I am simply multiplying the registers directly and putting the source or just loading the value into the source. So basically this example over here. So this one would be R9 will be equal to R9 times R10. Okay, easiest one to use. But it's good to be aware that we have all of these different versions available to us. Okay. So now we can move on to division. And again, we have to make a distinction between signed division and unsigned division. Unfortunately, unlike multiplication, we're stuck with a single operand version of division or integer division in assembler. So we have to cater for a couple of extra things, because if I have an instruction like idiv rbx, the immediate question is, okay, what is being divided and what is being divided by? So in this case, we're dividing a value by rbx, but what is that value? Now, actually what's happening here is we're dividing the register that is represented by two registers, rdx and rx, so we have 128 bits, divided by rbx. Now, in most applications, you don't actually need to store much in there. You might just be dividing two 64-bit numbers. But in that situation, you still have to zero out these higher order bits. So by default, 64-bit assembler allows you to divide a 128-bit number by a 64-bit number. So it's a little bit of extra functionality in a sense, but it also means you have to consider the fact that it's always going to be using that higher order 64 bits as well. So if I want to divide a 64-bit number by another 64-bit number, I have to make sure that though I want to load the value I'm interested in to REX, I have to also zero out RDX, which is a place where you can get some interesting errors if you're not being mindful of. Now, the same thing applies if I have smaller registers. If I want to, for example, use idiv EAX, let's say EBX rather. If I want to go idiv EBX, what is going to happen is that it's actually going to have this dividend stored into two registers, but it's going to actually be EDX and EAX will store the bottom 32 bits and the top 32 bits. So again, it depends on the size of the register that you're using. So now we know what the dividend is and what we divide it by. Where does the result get stored? Now, the first thing to keep in mind here is that this is integer division. So there's actually two outputs from integer division. If you were writing in a language like C++ and you divided something like 7 by 3, you would have ended up getting some kind of truncated version. You would just end up getting 2. Okay, but there are actually two components to a division. There is this, which we got now, which was the quotient, plus there's actually a remainder of 1. So it's what didn't perfectly fit into it. Now, if I perform division in assembler, I actually get both of those components of the division. I get the quotient, so in this case that would be the 2, and I get the remainder, which in this case would be that 1. Okay, now where they're stored is very specific. So the quotient will always be stored in RAX and the remainder will always be stored in RDX. Again, if I'm performing this kind of division, but I'm using, say, 32-bit registers, then the quotient will be stored in EAX and the remainder will be stored in EDX. Okay, so again, it kind of scales with the size of the register we're using. One thing also to keep in mind is that though in the case of addition and subtraction, we set flags, we do not set any flags with division. So we can't figure out what to do next based on a calculation if we just use division, as it doesn't set any flags by itself. Okay, so let's look at a little example to try and perform some division. So I want to divide x by y. So let's say I have x as a data quad, it's at 17, y as a data quad, so this would all be in my data segment again, it says 4, and I want to perform division of the two. Okay, and store the result in, let's say here we have a quote for quotient, and then we have rem for our remainder. So this is again just pre-allocated for us in our data segment in this example. So first thing I want to do is I want to load x into RAX, because I'm trying to fill this register over here. So normal move operation, move x into RAX. Then I need to set my higher order bits to be 0. So this part over here needs to be set to 0 because my value already fits into 64 bits. So I have to set that to be 0. Then I can perform my division. And because I haven't loaded y into memory yet, I'm just going to load it into register rather. I'm going to directly do the division from memory, and then I just have to specify the size. So in this case, y is a quad word, so I just need to specify q word. Okay, and this now it knows it's actually performing a 64-bit division. Perform this operation, and now I just need to extract my answers back out of those destination registers. So remember, the quotient went into RAX and the remainder went into RDX. So I just need to pull it out of RX into memory. And the same thing is I just need to pull the remainder out of RDX and put it into remainder. And I'm able to perform this kind of division. Now, for practical purposes, I highly recommend that you memorize the sequence in which these things get stored, because though you can kind of constantly be looking it up, you'll find that when we start doing more complicated code, it makes it very much easier for you if you have a good mental map of where all these source and destination registers are. So I highly advise you memorize this sequence. Okay. So now that we've actually done adds, subtracts, multiplication, division, so we basically are at the level of primary school with our assemblers so far, we can start doing something a little bit more interesting. So we don't have full conditional statements yet, in the sense that I can't have an if statement or a loop structure yet. We'll get there shortly. But we do have something that's halfway between the two. We have what's called a conditional move. So what will happen with a conditional move, so the CMOV is a conditional move, is that the move will only occur if some kind of precondition is met. So let's look at this first example over here, this CMOV Z. What will happen with CMOV Z is it will make a move only if the 0 flag is set. So remember before, if I subtracted two numbers and the result of that would trigger flags to be set, if the result of that computation was a 0 answer, my 0 flag would be set. And then if I had a conditional move after that, I would actually execute that move. Okay, so conditional moves only actually perform the move if the condition, in this case it's related to flags, is triggered. So this first one will only trigger if the 0 flag is set. We then have a couple more. We have a conditional move with NZ, so if the 0 flag is not set, so if our number is anything but 0 from a previous calculation. We then also have these variants, which is L, LE, G, GE. The justification for the mnemonic will be a bit clearer when we use compare statements, when we do proper control structures. But in essence, what this means is if I have a CMOV L, I will make a conditional move if the result of my last calculation was negative. Again, this is in a situation where the previous calculation was a flag setting computation like an add or a subtract. So if the last calculation, one of those, resulted in a negative, then this move will happen. This variant is if the last result, or if the 0 flag is basically set, or if the result was negative. So in essence, we're using the sign flag and the 0 flag. We then have the other side. We have conditional move G, where the move will only occur if the last result was positive, and GE for greater or equal to if the result of the last move was positive or 0. Now this comes up largely, and as I said, I'll explain this compare command more specifically later on. It's basically a subtraction that doesn't store the result. But if I have something like this, okay, what will end up happening is it actually subtracts RDX from RAX and doesn't store the result anyway. But the result of that computation can inform me over here. So for example, if RAX was greater than RDX and I said RAX minus RDX, I'm going to get a positive number, so it will trigger this one to actually perform the move. Now, again, don't worry too much about this. We'll get there. For the moment, just understand that these moves occur if the corresponding flags for them are in fact set. Okay. Now, one thing just to keep in mind with conditional moves is that the destination operand must be a register. Okay. The source register can either be a register or memory, but the destination has to be a register. So there's a little bit more constraint on a conditional move than with a traditional move, where I could store a value directly into memory. In the case of a conditional move, the destination has to be a register. Okay, so let's look at two examples of actually doing a conditional move. So the first one here is where I want to set a value to, in fact, be its absolute value. So first thing, before we look at how we do this with a conditional move, how would you do this with a normal high-level language? Let's assume you don't have an absolute value function and you actually have to implement this yourself. You would probably have to do something along the lines of, if, say my value, let's just use RAX as a variable in C++ just to make things clear. So if RAX was in fact less than 0, then I would probably need to change its sign. Okay, so I would need to set RAX to be equal to RAX times -1. And if this wasn't the case, what was stored in RAX would have still been fine, because if we failed to trigger this condition, it means it must have been equal to 0 or positive, which means it already is its absolute value. So that's how we would do it if we had a full loop functionality available to us. So we're going to kind of emulate that using the assembler. So the first thing I'm going to do is I'm going to save a copy of RAX. So I'm basically saving a copy into RBX. Okay, so I have a backup of the original RAX. Then I'm going to negate RAX. So in essence, I'm performing this operation here. I'm multiplying it by -1. Now this is where the conditional move comes up. So I've performed this operation, and now I want to decide whether or not I want to keep my RAX value that I just negated, or I want to reinstate the backup. Remember, RBX was the original version. So in this example, if the result of the previous calculation was negative, so when I performed the negation, I ended up getting a value that was negative, this move will happen. So basically, if I negated RAX and it became negative, it means it was originally positive, which means I've made a mistake and I need to reinstate my backup. So I'm going to move RBX back into RAX. If on the other side, I negate RAX and the result is positive, it means what is stored in RAX is in fact the absolute value of RAX. And then I don't want to replace RAX with the backup. I'm happy with the value it currently has. And in that situation, this command will almost act as if it doesn't exist. Okay, it does a check, but that nothing will get executed. You won't actually perform a move. So that's how we can use the conditional move to achieve the calculation of setting something to be the absolute value of itself. Okay, so let's try and do something a little bit more complicated now. Let's say I want to try and use a conditional move to do the following. I want to set RAX to be the maximum between 0 and x minus 100. So in essence, I want to pull x from memory, minus 100 from it. If it's still greater than 0, I will keep that value as my result. Otherwise, I want it to actually be 0. So let's do this with the assembler. So the first thing is I'm just going to load 0 into RBX. Then I'm going to load my x variable into another register. I'm going to load that into RAX. Then I'm going to perform my subtraction. So I'm basically doing this x minus 100. Now we want to figure out, are we going to use 0? Or are we going to actually use the subtracted version? So in this case, what will happen is we want to perform a conditional move. If x minus 100 resulted in a value that was negative, it will mean that this conditional move occurs. If x minus 100 was not negative, this conditional move will not execute. So in this case, where x minus 100 is, say, minus 3, this conditional move would execute, and we will load the value of RBX into RAX, which is our 0 value, which means we get the required functionality. If x minus 100 was positive, say it was 17, then this conditional move won't trigger, and will preserve the value that was originally in RAX after this subtraction over here. So now we are able to achieve kind of this if-like statement without having to use a full if control structure. There's actually a big upside to using a conditional move as opposed to traditional branching from a performance perspective. But I'll explain that a little bit later when we actually discuss how we can build an if statement, a complete and more general if statement in assembler. Okay. Something I want to kind of stress on, in our previous lecture, we discussed the notion of why registers are so good and how they're so much faster than working directly in memory or even cache. But there's a couple of things that I think are worth mentioning. The first thing is it doesn't pay to use a register explicitly if the value is only needed for one instruction. So what I mean by that is if I want to add a value from memory to a register, it doesn't necessarily help to move that value from memory into a register and then add it to another register. You should only be using register-on-register computations if I plan on performing multiple calculations using that value. Okay, so generally speaking, you don't need to worry about maximizing register utilization if something is executed infrequently. Okay. Now, generally speaking, the idea is that you want to use registers instead of memory for instructions which execute enough to matter. So there has to be enough frequency for the performance difference to make an impact. Now, this fourth bullet I think is very important for us. If I simply ask you to code something in assembler and I don't tell you anything about maximizing performance or anything, I just want the operation or the function to do something, or even in a prac, if I say you have to implement a function that does X, your aim should be for this course to always write code that is as clear as possible so that you can get the right answer as opposed to maximizing efficiency. Later on, you will start seeing some questions where I might say, okay, why is this approach faster than this other approach, or how can I make this approach faster? But your standard approach should be write code that is clear as opposed to trying to maximize all of these little bits of efficiency, trying to get little micro optimizations in. I would rather, particularly while you're getting used to assembler, write your code to be as clear as possible. That's what you're going to gain the best from, because the idea is to get the code to work correctly as opposed to it being a very efficient piece of non-functional code. So that's something to keep in mind. And I bring this up because with so many registers in 64-bit assembler, it is very possible that you can make code very efficient and it's not very clear. So while you're learning assembler, aim for things to be as simple as possible as opposed to as efficient as possible, okay? Unless I've asked explicitly to make something more efficient, rather aim for clarity. And I say this because though at first, these instructions we've gone through are pretty simple, it feels like you could maybe try and optimize the whole time, but you'll quickly fall into a trap where the actual code becomes so complicated and so convoluted when you're performing these optimizations that it's virtually impossible for you to debug efficiently. So aim for clarity while you're learning to program assembler. So that brings us to the end of today's lecture. And in the next assembler lecture, we're going to start going through some, as I mentioned earlier, bit operations. So we're going to start performing things on bit strings, and there's quite a lot of interesting things we can do in that context.